Consider an example where this is a tank and our objective is to maintain the level of water in this tank. This A0 is the cross-sectional area of the outlet of the tank. AT is the area of tank inside cross-sectional area, and we are pumping the voltage from this reservoir using a pumping water from this reservoir into the tank, and there is water flows out through this output. So for this to happen, it will not happen instantaneously, or this is an example of a dynamical system. Suppose initially consider the tank to be empty. So the more water we pump, more quickly the water pump, the more quickly it will get filled up. That means it takes some time. It is not an instantaneously, like the moment we switch on the pump it will not get filled up. It will take some time to fill up, whose level can be visualized like this. So the differential equation governing this particular system is given by this. The rate of change of filling up of water depends upon input flow rate Cp into Vp minus output flow rate divided by At. So for a given system, Cp is constant, Cp by At is and area of At and A0 are constant, and 2g are also 2g is gravitational constant, so they are all constant. So Cp by At is another constant, K1 into Vp. So Vp is the input, L is the output, minus A0 by At into square root 2g whole together put into another constant, K2 into root L. So this is the differential equation governing this system. So from this we observe that this is a non-linear differential equation because there is a square root term appearing for one of the variables, that is output variable. So how to linearize this particular non-linear dynamical system? So as explained in the previous video, we will get an wherever L is there we will put delta L, wherever Vp is there we will put delta Vp, because L is output and Vp is the input, and there is no nonlinear terms associated with this particular term, so we will retain as it is. But wherever a nonlinear term is associated, root L is associated, we will find its derivative and substitute that particular operating point, and we will make this delta L. Only then it can be made delta L. So this 2 into root L naught for a given level of the tank, this will become another constant. So we are calling K3 as minus K2 by 2 root L naught. So finally the linear approximation of this differential equation is d delta L dt is equal to K1 delta Vp plus K3 delta L. So the incremental transfer function governing this physical system is delta L of S divided by delta Vs is equal to K1 by S minus K3. This emphasizes so the main thing to be noted here is the non-linearity with respect to input and output variable. Like we are only differentiating with respect to this function with respect to L. So dou f by dou df by dl is 1 by 2 root L 0 at that operating point, and we should replace L with delta L. So the main thing to be noted is we are seeing the non-linearity with respect to input and output, not with respect to time. So this concludes.